We've talked about static electricity, which is a buildup of charge that doesn't move. But far more useful to us is current electricity. And this is what you're all so much more familiar with. You all know, if I've got a complete circuit and some kind of power supply, either mains electricity or a battery or a cell, then I can push electrons around a circuit. And that's so useful, as I'm sure you're aware. It's worth just talking about a few of the key words we need to understand. Firstly, current. Current is just a flow of electrical charge. Now, as we mentioned when we talked about static electricity, the only charged particles that will really move very much are electrons. So we often talk about current as being a flow of electrons because they're carrying electrical charge. We use the symbol I to represent current, and we will talk about it being equal to the amount of charge that flows past a point in a certain time. We use the symbol Q for charge and a little symbol T for time. So the charge going past a certain point per second, that's the current. The units of charge, the coulomb, or capital C, we always work in seconds. And the unit of current is the ampere, or amp. We just use a capital A for that. So that's current. It's how much charge is flowing around a circuit in a certain time. But you'll often hear people talk about voltage. Now, it's actually correctly called potential difference. But sometimes we will call it voltage, and that's perfectly acceptable. And it is measured in volts, which is where the name comes from. And we use the symbol V for potential difference. And it's equal to the amount of energy that every bit of charge has. So how much energy does each unit of charge have? Now, as I'm sure you know, energy is measured in joules, charge again is measured in coulombs, and voltage is measured in volts. If you like, the potential difference or voltage, this is how hard our battery is pushing, and the current is how much charge is actually managing to flow around the circuit. If we combine these two concepts, we get an idea that if voltages can produce different currents, there must be a reason for that. And the reason for that is something that we call resistance. Resistance is the opposition to current. It's how much a material tries to stop a current from flowing through it. So if you imagine for a moment, I've got a lump of metal, and this lump of metal has metal atoms, which are arranged fairly regularly because it's a solid, and between them it has some electrons, these little red dots, that are free to move. So if I've got a potential difference, a battery pushing those electrons, they'll start to move through the metal wire, which is brilliant. Suddenly I've got something that I can use with current electricity. But unfortunately, as you know, these metal ions that are left behind, because they've lost some electrons, they don't stay still, they move around. And if one of these metal ions bumps into one of the electrons, it will knock it off course. It will lose some kinetic energy. And that's what resistance is. So resistance in a metal is caused by these vibrations. And we'll call them lattice ions. They're the ions in the metal that are moving around, colliding with the electrons. It's really important that we understand this idea of resistance, because then we can start to understand how some different materials work and how some different components work in circuits. Now, we measure resistance in ohms, and the symbol for that is this Greek letter omega. And there's a really important equation which we call Ohm's law, named after the gentleman who developed this, and he tells us that resistance is equal to voltage divided by current, or if you like to put that into a triangle, it will look something like that.